Yeah, thank you. Today we'll talk about how to get started with multi-GPUs and give a bit of an overview of what are the paths that you can take. Typically, if you already have your sequential project and you want to move to multi-GPUs, there are, of course, many paths, and some of them are more challenging than others. I'll try to pick up some of them in this presentation. For some motivation, why multi-GPUs? And it might be obvious that with the data growth of this exponential data growth we have been seeing, we expect that more and more will have to use multi-GPUs in order to handle these data. Of course, the memory on GPUs increases, but in many cases, it won't keep up with the growth of the problem sizes. So you would need to use multi-GPUs just in order to have enough device memory to handle your problems. And of course, another thing is you can add or decrease the computation time, and often you would have to use multiple GPUs for that as well. But I think primarily it's because of the data size just keeps increasing. If we go back in history and look at when CUDA started, in a single GPU case, what happened was CUDA was introduced, and people were starting using CUDA for small areas in their code, so they had some bottlenecks, and they would optimize for that bottleneck. So you would have your program running primarily in the GPU in main memory, and then you've got some areas of code that you want, I can optimize that, re-implement that in CUDA, move it back to the GPU, and do the work there. And later you had libraries saying, this library is CUDA accelerated, and you can use that. But the main gate between the libraries were primarily CPU and CPU memory. And so you would have a flow like this, where you started with some I/O, CPU did some parsing of that I/O, and then hand it over to CUDA and to device memory. And then probably, if you wanted to use another library, you would go back and forth. So you would have this back and forth between device and host memory. But nowadays, this single GPU ecosystem has evolved to a case where we have a broad range of accelerated libraries, and they can talk to each other. So you can actually, nowadays, you can access the files, move them directly into the device memory, bypassing more or less the CPU completely, and do all the work on device memory. And even if you're using multiple libraries, those might often have zero copy compatibility, so you can just hand over data from one library to another. Now, going multi-GPU, that ecosystem isn't that evolved for now. So we are more or less back to the start, where you can read in again in a CUDA library, accelerated library, using multiple GPUs. But if you want to use other distributed libraries, you often have to do some manual redistribution of data. And that's a big issue, because that can be very, very expensive. And this is maybe one of the reasons why going to multi-GPUs are very difficult, or more difficult at least. But we're hoping that at some point we get to this unified frameworks where distributed libraries also can talk to each other and be compatible. And I will show in this talk an example of such frameworks. But it's not the general case at the moment. It's still something that has to be evolved. Now, if you want to use multi-GPUs, you have to use some libraries and tools. And so here I've plotted some programming languages for multi-GPUs. And so at the x-axis here, you have how domain-specific is the library, how general is it, and on the y, you have the productivity or ease of use. So broadly speaking, you want to be up here at the upper right corner, where your library is perfectly general and is extremely easy to use. And vice versa, you don't want to be down here where it's very specific and it's very hard to use. I should say that these different examples of libraries are plotted in here are, their location on the plot here is fairly subjective. I'm sure if you ask the individual developers, they might disagree a bit. But the overall idea here is just to say that we have this diagonal of different libraries where you have to, there's a trade-off between how general is it and how productive, how easy of use. Today, in this talk, we will focus on these more high productive, higher level abstraction libraries. And we'll be talking about CuPyNumeric and Dask-cuDF, and give some examples of also some of the others. The next talk at 9 a.m., also in here, Monolith will talk about a more lower level, less abstract program model where you get more control, but also arguably a bit more difficult, a bit more work to do. And then finally, Jiri will talk at 10 a.m. We'll talk about the more raw communication libraries, so where everything is much more explicit. And of course, these libraries work together, and so you would often see that the more high-level libraries uses the low-level libraries for its communication and orchestrating of the data distribution. Another way to categorize these different parallel libraries are that data parallelism, if it's explicit or versus implicit. And that's probably one of the main questions you have to ask yourself if you want to use multiple GPUs. What model do you want to program in? In the explicit case, the framework exposes the parallelism to the user, to the programmer. And so you often have some kind of a SPMD-style programming, some MPI-style programming, where you have multiple processes, typically one per GPU, and then as a programmer, you know that your program is running on each process, and you would have to orchestrate and do communication between those processes. And the advantage of that is it forces the data distribution and parallelization on the programmer. So the programmer would have to know how are my data distributed, and that's a good thing in the sense that that makes it easier to be compatible or make compatible with existing libraries and the ecosystem of existing, so say, MPI ecosystem, which is huge. Now, the downside is that you would have to learn this program model, and you would have to be more or less expert in MPI or something similar in order to use. In an implicit case, we are moving most of the parallelization to the library. And so the user won't have to worry about that. That's great because you get this sequential control flow that as a programmer you write as if you were writing sequential operations. So basically a sequential program, and it's the job of the library or framework to infer data parallelism from those operations. That makes it high productive, and it's by isolating the programmer from the parallelization, the framework gets a lot more freedom to optimize. It is the framework that's the library that decides where data is distributed and so forth. Now the downside is that it's hard to reason about performance because it's not explicit, so you don't really know, you might not know what's going on behind the scene by the library. And similarly, you might do some operations that seems to be working fine on a single GPU, but when you're scaling up, the performance degrades more than you would expect. Some examples for explicit data parallelism. I have here an example of doing a distributed matrix multiplication and using 3 different libraries. So the first one we have MPI, and here I'm just using MPI for Pi, so we're writing in Python. And we're using CuPy, which is a NumPy accelerated library, so basically NumPy running on GPUs. But since in MPI everything is explicit, so first off you know that this code will be running on each process, and so you will have to consider that, and you have to make sure that there's no deadlocks and the communication pattern and so forth. And similarly, all the data in your code here will will be pointing to local, basically local data. And so it will be a job for the programmer to do all of this kind of orchestrating of this computation. So in this case here, I have to worry about what rank am I in the process, how to divide the world, how am I going to distribute and decomposite my data. I need to initiate some communication patterns. In this case, I'm programming a Cannon's algorithm, which is a block matrix, fairly efficient algorithm where you have blocks in the matrix and then you shuffle those blocks around. But the point here is that everything is manually. The only thing I really get from MPI is that it is device aware or CUDA aware. So when I provide these CuPy buffers, CuPy buffers, MPI will automatically handle those device buffers. And so if you're sending from one GPU to another, it will handle that. And that's something that Ye will talk about at 10 a.m. here. In the second example, we have a QBLAS MP. And QBLAS MP is basically BLAS, so this old linear algebra library that are accelerated, so QBLAS are running on CUDA, and then MP for multiplexing. So it's linear algebra on multiple GPUs. And this one is in C, so it's a bit more verbose, but the idea is the same. Now we have to worry about these grids of GPUs. We have to describe to the library how our data distributed. We can ask for some buffer sizes we will then have to allocate. And then finally, we can call this matrix multiplication using these things, right? So you describe what you have, your world, to the library, and then the library will handle the matrix multiplication. So that will be the black box. That's the abstraction, right? So we don't really know what's going on inside there, but it just runs, and then it tells, oh, now I'm finished, here are the data. And you would have to access those local buffers. Final example is this PyTorch distributed, where PyTorch is a very popular machine learning huge framework. And it also has a distributed version. And that one has this distributed tensors, and you also have matrix multiplication there. And now we are much more abstracted, much of the detail are abstracted away. We still have this device grid, or it's called some mesh here, but we can just generate some random tensors and do the matrix multiplication, and the diff framework will handle it. So there are different abstractions levels in the explicit data parallelism. If we go implicit data parallelism, one project we're working on is CuPyNumeric. And CuPyNumeric is basically accelerating NumPy to run on GPU using CUDA and running multiple GPUs. So it's a full package, basically. And so here I have a conjugate gradient solver written as you would write a regular NumPy application running on a single CPU. In order to use CuPyNumeric, I'm importing CuPyNumeric instead of NumPy, but that's actually the only change I need to do. So in this case, CuPyNumeric will infer data parallelism from these operations. So those are all reference to distributed data running on multiple GPUs, and by a lazy evaluation of this program, CuPyNumeric can infer data parallelism. And you should know this is sequential user code, right? So this code, as it runs in NumPy, if I run it in CuPyNumeric, it's running on a single machine, single Python interpreter. And so they're all, it makes it much more productive because all of the parallelization issues, you don't have to worry about deadlocks or how to do communication peer-to-peer. So you cannot even do communication peer-to-peer in this at the CuPyNumeric level. it has control for duplication, so this code might actually run on multiple GPUs, but as a programmer, the program model is a sequential one. So you only have to worry about the sequential code. A not so fair comparison, you say comparing CuPyNumeric versus NumPy. And it's not so fair because we were comparing a NumPy single CPU execution versus 8 GPUs. But it's still interesting or relevant because that is something you can get without changing any code, or only a few import lines, import statements. And so you might not get as good performance. There might be some more advanced things you're doing, but it's a motivation at least to check this out, because using CuPyNumeric to check what's the performance, and it might be good enough to what you want to do. If you go into a bit more detail, so here I have some fairly trivial example where we import CuPyNumeric, generating 2 random vectors. But at that point, when those commands are executed by the Python interpreter, no computation is happening. So what we'll do is CuPyNumeric will track the operations, but won't do any computation as of now at this point. So we can ask for the type, we can do an element-wide operation, just like you would do in normal NumPy. In this case, you get a result. We can ask for the shape, and again, the shape is just metadata. We know the shape without doing computation. So that's something. And then at the final state, I'm doing a sum of this result and printing that to screen. And this is where CuPyNumeric says, oh, now we need this scalar value, this sum, to the user. At this point, we need to build the graph that was extracted from lazy evaluating these operations, apply that to the distributed data. It's up to CuPyNumeric how it wants to distribute these random vectors, depending on their size, how many GPUs do you have, and so forth. And then finally, you send the scalar to the Python interpreter, and it will be printed out. So that's the program model. And CuPyNumeric is part of the Leagate ecosystem. It's using Leagate as its backend. And that's very valuable because that means anyone using Leagate as its backend are compatible. So we have CuPyNumeric and their work on other projects like Leagate DataFrame, ML, and so forth, all using the same primitives. So all using Leagate as its backend. And that means Leagate, so for instance, you could take CuPyNumeric array, a vector from before, and copy that or move that into a data frame column with 0 copy. And in fact, if you're using the same primitives, Leagate will have a chance to optimize across library borders. So one operation in one library and another in another library can be optimized and maybe fused together and stuff like that. So it's very powerful to have this common primitives for your libraries. Another implicit data parallel library I want to talk about is this Dask-cuDF. And Dask-cuDF is a GPU-accelerated pandas. And pandas is a data frame library that's very popular in Python. And Dask is a distribution of that. So that Dask is the multi-GPU part, and cuDF is the acceleration within a single GPU part. And in Dask, what you can do is you can say, by default, it will use pandas. But we have this configuration, and you can define a new backend and say, you know what, I want to use cuDF as my primitive instead of pandas. And so all operations will now be accelerated using GPUs. And again, it's running as a sequential code, just like in CuPyNumeric. All the parallelization are inferred by Dask and cuDF. In this case, they have some housing prices, US house prices that on a remote server, I can do a read CSV, and that will run lazily. So again, nothing happens at this point. Dask is just gathering the operations, and we can do some group by state, some price, and calculate the mean. And then we get to compute. And it's at compute that you say, oh, now I need this values to this Python interpreter where I'm running. And they'll have Dask generate this task graph of CuDF operations. And then in this case, moving this mean back to the Python interpreter and print the result. So very similar to CuPyNumeric. It's a bit more explicit because now you have to say compute, but I mean, there's very minor things you have to do. Dask-cuDF is quite good at memory spilling, so it will automatically move data from GPU to host memory or from host to disk based on your memory limits. So either you have some threshold, say you want to use this much memory, or it will do that automatically if it would otherwise run out of memory. And also a bit not so fair comparison here. We are looking at Nemo Curator, which is a pre-processing to LLMs. It does some deduplication of tokens or passing input basically before generating the tokens. And by using Dask in combined with CuDF, they are able to get very good performance. Again, it's not so fair comparison. We're comparing with a CPU library. But the overall trend is that doesn't require too much work. You can accelerate your code. And Dask-cuDF is also part of an ecosystem. So here we have the Dask data frame. There's also Dask SQL, XGBoost, and a lot of other. It's actually a quite broad ecosystem, Dask. And most of them, or many of them, have accelerated CUDA backends. Now, when you go the implicit route, what do you do if it's not perfect? What do you do if the framework can't handle your problem? And the first thing people probably fall into this common pitfalls, where you're programming as if it was sequential. So there might be some pitfalls that you get into because you're thinking in sequential code, and that's kind of the that's a problem with when you do everything implicit. So one example here. So this example is from CuPyNumeric. So one here you have avoid loops with indexing. That's if you're a Python programmer and using NumPy, you will know this. That if you have an array, you shouldn't use Python loops to iterate through that array. Right? You should use NumPy operations, and the same goes for CuPyNumeric. You should use CuPyNumeric operations. So in this case here, instead of extracting part of y and moving into x, we can use NumPy's slicing semantic to get this single array operation, and that means CuPyNumeric will know how to do that operation in one go. Another thing is advanced indexing. That's a bit more tricky, and that might not be obvious for a programmer. Is if you have, say, you have an array, and now you want to find all the indices where something is true, for instance, that age is negative. That means that's a perfectly fine thing to do on a single GPU, because you get this out result of indices. Then you take those indices and you can index with them. Right? That seems very reasonable. But it turns out that if you do that in a distributed setting, it's much more difficult to CuPyNumeric to do this efficient, because now it has to produce these indices, and that will be a new array distributed between many GPUs, and so you end up doing much more communication than you would do if it was on a single GPU. So that's something that, you should, in this case, they are recommending, you should use Boolean mask instead. And finally, an example here is if CuPyNumeric is compatible with NumPy, it's also compatible with SciPy. So what you can do is, I want to do a Cholesky decomposition. You might say, I know SciPy, I'm just gonna use SciPy to do that. And it works. But it means now the matrix here, which can be huge and distributed, will have to be gathered automatically by CuPyNumeric, but still will be moved back to one GPU and even, in this case, the CPU, and to do the operation. And so if you don't have enough space on a single GPU, it will just fail. And if you have enough space, it might be very slow. So that's a pitfall. In this case, it's fairly easy. You can just CuPyNumeric actually has a Tedeschi, so you can just use that, and then it works perfectly. What happens if, okay, so you avoid these pitfalls, and now you're using CuPyNumeric, but for some reason, either there's something that is not supported, so you don't have that operation you want to do, or the performance you're seeing is just horrible. And so what you can do is, there are two approaches, basically. The first one is to, as we did before, interpret CuPyNumeric arrays as regular arrays. And it even support CuPy. So down here, we have these vectors. I can say, interpret this vector as a CuPy array, and it works perfectly. I get a local vector. I can do my local operation, and that, in this case, printed the sum. But again, because we're doing a distributed setting, it will have to move this vector that might be large. If it's small, it's fine, but if it's large, you have to move that to a single GPU and do the operation. So to get good performance, you would have to bypass CuPyNumeric and use CuPyNumeric's backend Legate. So this is the same operation, but now I am defining a new task that are Legate tasks that Legate knows how to distribute. Monolith in the next talk will go more into detail here, but just to give a feeling, I have the same operations. I can do this vector thing, and then I can call my custom task, and I define this task saying, oh, I want this to run on a GPU, and I get to have these input or output arrays, and you can even add constraints and a lot of semantics to define how this task wants its input. But when that's defined, that task can run across multiple GPUs, and is compatible with all the other operations in Legate. So it is possible to, so if you're stuck, it's possible to get around that by writing your custom code. But of course, it's more difficult. Right now, you have to know more about how Legate works. So that's kind of the trade-off. For Dask-cuDF, it's the same thing. We can again fall back to a single GPU using compute. So in this case, I'm just saying I have this local data frame. Give me a copy on my local execution, this Python interpreter, and it will work fine. But if I want good performance, if the data frame cannot fit my single machine, I can write again a custom task and use this map partition. In this case, basically what you're saying is, please Dask run this task on each block in my data frame. Again, if more detail of these tasks, Monolith will talk about next talk. So to sum up, what framework should you use if you want to go to multi-GPUs? The good news is that it's not mutually exclusive. You can combine abstractions levels, and that would primarily recommend going from the highest abstraction and start there and see where it fell short, and then only at that point write more low-level code. If you look at the explicit data parallels route, it's great if you already know MPI, or if you have existing code base using MPI, or something similar, some SPMD model. Then explicit route is great because it's fairly easy. It should be okay to create and make them compatible, basically, and maybe even support zero copy. And if you have to do a reshuffling or re-interpreting of data, you know MPI, so you can do it, right? So you have the tools using MPI, or what SPMD model you're using. You have the tools to redistribute the data. And typically, you would also probably get the highest performance. Depending on how good you are to program, of course. Now, the implicit route if you want high productivity, if you run a sequential code, all the bugs associated with parallel programming it's not possible to do, right? So that's a huge thing. Going from a single to multi-GPUs, all the complexity of sending stuff from one process to another, synchronizing all that, logs and all that, it's completely gone, right? Everything is inferred and handled by the framework. And a very obvious case is if you have existing, say in this case for CuPyNumeric, if you have a NumPy application and you're happy with that, then you maybe accelerate that using CuPy. Then the next step could be try CuPyNumeric. And with very little code, actually there is a custom launcher where you don't even have to change anything. You can try it out, right? See what's the performance. There might be some performance issue in some operations, or there might be some operations that you don't support, CuPyNumeric doesn't support, but then you have to look into the custom task. But just know that even if you're stuck in something that doesn't exist, it is possible. There is an escape hatch. You can write your own custom task. It's also great for implicit data parallelism for larger projects. It's nice because you can abstract the different groups. So you have your domain experts that are primarily using the library and developing a tool for data analytics or whatever. You can isolate them from the parallelization, typically computer science experts, and have the library handle that parallelization. So that makes it very powerful for maybe not if you have a team of domain experts and parallelization experts. Yeah, and I would point some. There are some examples down here. And other than that, this is part of the CUDA develop sessions. So there are some other blogs for how to use CUDA, how to go multi-GPU. That's not it.
I think we have some time for a few questions. Would anybody like to ask? Okay, right here.
Thank you. Congratulations on your presentation, first and foremost. As convenient as this implicit thing is, can I ensure in some degree that it is running on multiple GPUs? Like, is there some safeguards, or can I check the number of nodes that it's connected to, the number of GPUs the job has been distributed to?
Yeah, so that depends, of course, on the framework, right? But both
CuPyNumerics.
So both Dask and CuPyNumeric has a broad range of profiling tools and monetization, so you can see stuff like that. Of course, if you're just using CuPyNumeric and you're not providing any information, you're only providing how much memory will be used and how many GPUs, how exactly that is distributed is up to the library, right?
I just want to be sure that users are not taking a day to run because they don't know it's running in a single.
Oh, in that case, so there are some tools to do that.
Perfect.
Again, great talk. My name is Prit Banerjee. I'm CTO at ANSYS. ANSYS does a lot of work on GPU acceleration. We have actually taken our fluent CFD code and parallelized with multi-GPUs using MPI. The question I have is, Jensen in his keynote speech talked about Grace Blackwell and the coherent shared memory that is existing now. In the past, as your first slide showed, you have to do memcopy from your CPU memory to GPU memory. It's very ugly. With all the NVLink and all the latest stuff that is happening between coherent shared memory, apparently it looks like this is the memory on the CPU, and you just do a pointer and you do whatever computation. So it is becoming ease of use. So the question I want to ask you is, I'm not talking about using CUDA library. I know this is library talk, but in terms of, can I use that coherent shared memory as like a distributed shared memory? You know those machines like Kendall Squares used to be there. I assume you are familiar with it, right?
Yeah.
And get up to 80% of a performance of a hand-coded multi-GPU MPI implementation. Are you getting my question?
Yeah. So the question is if you as I understand, so if,
how automated is
Yeah.
coherent shared memory?
So it's true that these new architecture has this unified and coherent memory. So the host memory and device memory can access both, and the GPU can access directly. But to get good performance in your program, you would have to somehow tell the runtime system that what you're doing, the memory patterns, your access pattern. Otherwise, performance won't be good. And that is more drastic if you're going to access remote memory. So I think it's a way to get started, but it's probably something that you would have to, while developing, you would have to give hints of prefetching, and you can drop pages now in new CUDA, stuff like that, where you're basically telling the runtime system, oh, now I'm accessing on remote. That should be prefetched and not wait until my critical loop in some kernel, right? Because that's going to be horrible. So there is it still requires a lot of work, even though it's all unified.
Thank you.
Any other questions?
Okay. Thank you for your nice talk. And can you mention a little bit more about a performance comparison between explicit method and implicit data parallelism? And of course, it depends on algorithm and problems, but
yeah. So it's hard to generalize, but of course, if I'm doing something explicit, I can always mimic and do the same that. So, for instance, CuPyNumeric. So, if CuPyNumeric is doing something or Leagate is doing something, I could do the same thing if I'm rewriting that in MPI or NVIDIA or some other library. But the question is, can you do that, or how much work will it take, right? So that's why, in many cases, explicit are more performant if the program is good and are forced to think about data locations. It's a bit about in relation to the previous question is, if you just let the framework do everything, then it might be tricked into to do something inefficient. But this again where in CuPyNumeric at least you can write your own custom kernels, and those constraints can force the runtime system to divide and distribute your data in a particular manner. So yeah.
Thank you.
Hi, Jeff Mulmer from ExxonMobil. You mentioned MPI, but one thing I didn't see there was nickel. Can you talk about MPI versus nickel? Is ever a case where you would mix MPI and nickel communication libraries?
So nickel, if you're not familiar, it's just very primary. So basically, it's first off device to device, where MPI is more general for both for host and device memory. Nickel has these very nice collective operations. MPI has as well, but I think you can mix them. And the talk at 10, we will talk about more in detail of these communication libraries, what advantages they have. Yeah.
Thank you.
Actually, to add to that, Yuri's talk has been moved to room 230B down the other side. So he needed a bigger room because the topic is so much more popular. But great question. Any other questions, please? Don't be shy. Okay.
Yeah, Newman here. Thanks for the nice talk. So a little bit of a specific question on CuPyNumeric. Is it sort of topology aware, like MPI? Can you talk a little bit more about how do you handle sort of distribution, shared memory, etc.?
Yeah, so the program model itself doesn't say anything about that, actually. So as a programmer, if you're using CuPyNumeric, it's up to the framework to do the distribution. Mm-hmm. But then what happens is it does what you will do also in MPI application, right? So you have a topology of the GPUs divide. So in this case here, you have some thresholds of how big stuff are, how many GPUs do you have. What it will do, and what's the hard part, but also what the clever part is, it will look at the dependencies between your different operations that are generated, and that's why also you need this lazy evaluation, because then you get more information of what operations. Then it will see, oh, in order to minimize communication, these paths should be the same, or we should need this kind of borderline, or
And follow up, if I can. So do you do any ahead of time, or is this entirely sort of like lazily executed? Like, for instance, just to say reduce, sort of like, you know, taking the graph and going through all that.
So CuPyNumeric will, for instance, reduce, will use primitives in Legate that supports reduce. And so you have this, you can build this tree of reduction. So all of these things, all these tricks are kind of the same. So the only problem is if for some reason it doesn't match up. There's also, when we say it's lazy evaluated, but in reality it actually has a front. It looks so there is a maximum number of iterations that will be tracked until execution will start. And that
Thank you.
I think we have time for one more question. If not, you can meet with Mads outside too, and he'd be happy to talk to you more closely from a one-on-one perspective. So thank you for joining the session. Again, the recording will become available within 48 hours. Please, if you want to win a $50 gift card, fill out the survey in your GTC app and give us your feedback. So really appreciate it. Thank you very much. And thank you, Mads.
Thanks.